So today, so far we have been looking at how to parallelize loops, and we didn't look at the task parallelism, but definitely you should look for task parallelism. Like for example, if your program consists of two tasks that can be done independent of each other, you should go ahead and try to achieve task level parallelism. So we used roofline analysis to as a theoretical tool to see where we stand in terms of performance and where we should put our effort to gain better performance. Like when we do roofline analysis, we will know whether we are compute bound or memory bound. If we are memory bound, then we may want to use some optimization strategies which help in improving the locality properties of the program so that the effective bandwidth, memory bandwidth increases. And if it is compute bound, and if you are using SIMD and if it is just compute bound, then maybe you can use more threads, because when we use more threads, then the compute roofline will go up. And if you take a deeper analysis, let's say if you're hitting even the roof also, if you take a deeper analysis, you might not be using FMA instructions, fused, multiply, and add instruction. But if you use fused, multiply, and add instruction, perhaps you might be able to increase the compute roofline a little bit more. So that's a very, very important tool, because when we try to optimize programs, we should not be shooting in the dark, okay, blindly doing things. We need to understand, so what is the problem, what is the bottleneck, and how we can address the bottleneck. So that's the most important tool that we have studied together in this course. Now in today's lecture, we will see another theoretical tool which is good for our to understand whether we are doing the best or it's a different perspective. Okay, so in the first 1 hour of today's lecture, it's more theoretical. In the second half, we will switch gears, and I will try to introduce you to ideas which we didn't discuss, which we didn't get time to discuss in the course. Okay, but they are important ideas. So that's the plan for today's two-part lecture. So let's get going. So most of this, the first part of today's lecture, it is based on research done at MIT by Professor Charles Lisserson's group. And they built a system called as Silk, C-I-L-K. We will see. Maybe when it comes to that, I'll explain it a bit more. And there is a course on MIT OCW on programming for performance. So if you want to dig deeper and understand aspects of this bit more, that's the place to go. Well, so this is Fibonacci code, and these slides are also based on Professor Lisserson's lecture notes. So this is the code for Fibonacci, and this is a recursive code. And yeah, of course, this is a bad code, because you end up computing, calling Fibonacci with the same parameter multiple times. So when dynamic program is introduced, this is used as as the toy example using which we motivate the dynamic programming. So yeah, but the good thing about this code is it is easily parallelizable. It's, if you think about it, So Fibonacci n is you compute Fibonacci n minus 1 and you compute Fibonacci n minus 2. Whatever the results that you get, you return back to Fibonacci n, and it will sum them up and it will return. Okay, so it will return to whatever the function that is calling it. So you can clearly see there is a task parallelism that you can compute Fibonacci n minus 1 and Fibonacci n minus 2 independent of each other. So it's great. So if you want to parallelize this using p-threads, you want to parallelize this Fibonacci code, basic Fibonacci code using the p-threads, then this is the code. Okay, so let's not get into the details because the intent here is not to introduce how to write programs using p-threads. It just shows it's too complex. Okay, there's quite a bunch of code that you have to write. Broadly speaking, here we are creating one thread, and then there is another thread. So here you spawn a new thread, and there is another thread which just continues. And in that thread, we are computing Fibonacci n minus t is computed here. And using this thread T1, you may compute Fibonacci n minus 1. And then there is a join here, which kind of syncs up these two threads. And then finally, you do the computation. So that's roughly that is what is happening here. But the problem is the code is too complex. I mean, if for a simple function like say, Fibonacci, if the code is this clumsy, then as we try to do more complex things, this becomes much more harder. And then, so in this, we didn't study about Intel thread building blocks. So I will post a video which I would like you to watch. Intel, and in the project, I would like you to seriously explore if you can using Intel TBB makes sense for you. Okay, Intel thread building blocks. So, well, if you use, again, this looks a bit complex, but perhaps better than this TBB is based on C++. The host language is C++. And if you are a good C++ programmer and TBB uses what are called as thread pools, it uses thread pools and I think what is called as a work stealing scheduling strategy, to so what happens is when like when you create threads, there is a lot of overhead in creating these threads. But instead, and also you may, if your system may have 12 cores, if you end up generating, let's say, 20 threads or 30 threads or 40 threads, then what happens is you end up oversubscribing to the hardware, and there will be a lot of context switches. And whenever there is a context switch, the cache gets polluted, and there is a context switch overhead. All these things will have a serious penalty on the performance of your program. When instead, if you use a pool of threads, like for example, if you have a 12-core machine, you can use a pool of 12 threads or 24 threads. Or if you have a 64-core machine, you may want to use a pool of 64 threads. Then, and this thread pool will always be there, and they just pick up work based on what is the available work that is out there. So that way, the overhead in creating threads will be reduced. Number one. Number two is you don't end up doing oversubscription for the hardware. You see what is available hardware and how many threads make sense, and you can pick the so that is you can choose the thread pool size based on the available underlying hardware resources. Okay. There are a bunch of other advantages using TBB. So yeah, so please, I will post a video. Please watch that video. Whether you use it or not, use this as an opportunity to to learn a little bit about thread pools, thread building blocks. So that way down the lane when you're solving a problem, we can consider it as an option. And seriously, for your project, you should think about it. Okay, whether if you can use thread pools, Intel thread building blocks for solving the problem. And of course, this is OpenMP also supports task parallelism. In the earlier versions of OpenMP, like OpenMP 2.0 or 1.0, there is no support for task parallelism. But in starting from OpenMP 3.0, there is support for task parallelism. So here, so what happens is, intuitively, the statement immediately after that, a task will be spawned and Fibonacci n-1 will be computed there. And then another task T2 will be spawned and Fibonacci n-2 will be computed by the task. And then this is a task weight is a synchronization barrier because you can only compute x plus y only after both Fibonacci of n-1 and n-2 are computed. So we use this as a barrier. So this is about OpenMP. If you do it using OpenMP task parallelism. Needless to say, you need to explore a bit more on what are all the available options there in OpenMP to exploit task parallelism. Okay, keep this also in mind when you are working. You can either use TBB, or if you feel using OpenMP is much more easier for your application, you can go ahead and use OpenMP. So one thing that I would like you to, which we didn't quite discuss more well in the class, is what is called as a nested parallelism. So like, for example, there is one thread which spawns multiple threads. And and you in turn call another function, and this one again spawns multiple threads. Okay, that is in a parallel thread you are spawning many more parallel threads. And if this nested parallelism is not, what is the semantics of nested parallelism, be it in OpenMP or TBB or whatever the framework that you are using, you need to be aware of it. Because it will have an impact on the performance of your program. This nested parallelism. And TBB handles nested parallelism well. And in OpenMP, you have to see, I didn't check how OpenMP, kind of works on nested parallelism. You have to check. Okay. I'm giving you some pointers because all these things, you should try to explore them on your own and learn when you're working on a specific problem. Okay. In OpenMP or? Nested parallelism. Yeah, if it keeps spawning threads. If it keeps spawning threads. You want to manually do it, and then if it tells the thread to keep spinning, get the scheduler and the priority of this thread is very good. Okay, I see. Okay. And then we have Silk. So in Silk, so what you do here is there are few keywords. You can annotate your C program or C++ program using the keywords such as Silk spawn and Silk sync. So when on here, so here you spawn this new thread, Silk spawn fib n-1, I think they are using the word, the named child function may execute in parallel with the parent caller. The reason is the silk scheduler will decide, I guess, whether it makes sense to spawn a new thread or not, or something like that. I'm not sure. But if you kind of leave that aside, so here there is a main thread that is coming, and then when there is a spawn, so this in this spawned thread, fib by n-1 will be computed, and in the original parent thread, fib by n-2 will be computed, and then there is this silk sync where both the threads will sync up, and then the computation proceeds. So, so one interesting thing here is the amount of code changes that you have to make for your program in order to use this silk and parallel computation framework is very small. In fact, they say there is a suggestion, like for example, you can simply say you can write serial code, and you says hash define silk span, you don't have anything here. Similarly, you can have hash define silk underscore sync. So what you do is you have these macros, and you define these macros to empty when you are trying to run this code in a serial fashion. You debug your code in a serial fashion. When you are debugging your code, the serial code, these silk underscore span, silk underscore sync, they are they are defined to empty things. That means effectively you are removing them from the code. And then again, you invoke when you want to, once your serial code is debugged, you put these, you enable, no, you kind of remove these macro definitions by using an appropriate compilation flag. Then then that means now your program can run in parallel, because these keywords, they tell the silk runtime environment. So there is, along with this, there is what is called as a silk runtime environment, and that silk runtime environment will manage all the threads for you. And silk, again, it handles nested parallelism well, and it has what is called as a work stealing scheduler, which maps these computations to the available threads on the system, so that the computations happen efficiently in parallel. So there is a lot to silk runtime environment, and so usually, when we write parallel programs, the problem is the bugs that arise because of the non-deterministic execution or non-deterministic overlapping of threads, instructions of threads. And silk provides these guarantees that, like if there is a bug, it can help you to trace the problem. What is the problem? Usually that's a big challenge in parallel programs. Like any bug, we want to reconstruct the path which led to that bug. Only few frameworks guarantee that, and there's a lot of research on that, but apparently it looks like silk has that property that it can give the path which led to that particular bug. So there's quite a bit of theoretical research which we are going to study in today's class from Professor Charles Lisserson's group, and they built this silk parallel programming framework. It consists of keywords such as this, which we insert in the source code, and also there's a runtime environment which does all the scheduling. They call it as work stealing scheduler, which is near optimal. Okay, which is they have a near optimal scheduler for this. And Intel acquired Silk probably a decade back, and I think there is a support for Silk even in the GCC compiler. But for some reason in 2017, Intel stopped supporting Silk, and they said, no, it's no longer, we have to use TBBs instead of using Silk. And I don't know the exact reason. So I think what happened after that is now there is what is called as an open Silk version, which again, the MIT group is trying to push this OpenSilk version. It's not supported in Intel, but they are trying to push it in. Yeah, this OpenSilk, they are trying to do it in the LLVM compiler infrastructure. So that means you have to use Clang or Clang++ in order to use this. ICC adopted? Is it? Why would they do that? Actually, they are not. They are saying don't use ICC. Actually, they have what is called as a DPC++ compiler, and they are saying use DPC++ on. DPC++ perhaps uses LLV. Okay, but again, this is an important reference. I'm a bit fascinated about this Silk framework for the ease with which you can parallelize your code and the kind of analysis it gives you, performance analysis it gives you. You are not looking into it deeply, but it can give a lot of good analysis on how best your program is executed. But the challenge I found is OpenSilk. It looks like it's not easy to use. So I tried a bit and I had some challenges, but I didn't spend too much time. Finally, I pulled a Docker image they have and tried to use that. So those of you who want to again use it for your project, please feel free to do so. Otherwise, also keep this in mind that this is an option that you can use, and it has a lot of good, nice tools, associated tools, which could help in which could come in handy for you. And you can parallelize loops also using Silk. So you have to use silk_for keyword. That's it. So the outer I loop is parallelized. Yeah. So as I said, so there are two aspects to it in the Silk computing computational framework, parallelization framework. One is you go to the source code and you use these keywords for parallelization, and the compiler uses these keywords in order to generate appropriate code. That is the compiler part of it. And there is a second thing, that is the runtime. Okay, and the runtime is what does all the scheduling of the threads and mapping these threads to the available thread pool and so on and so forth. And the last part here is important. Silk's work stealing scheduling algorithm is provably efficient. It is near optimal. Okay. So that's what they claim. Okay. So all good so far? Yes. So now let's try to understand the theoretically a multi-threaded program, how we can go about analyzing a multi-threaded parallel program. So if you have a multi-threaded program, then we can look at that parallel program, or even let's say if it is not parallel. Let's say if you have a program and you can look at the computations in the program by constructing this directed acyclic graph. So here, so that the idea here is, so in this directed acyclic graph, so if you want to do this computation is ready for execution after the predecessors have finished execution. Okay, so it's a dependency graph. This is a dependency graph. And for the sake of simplicity, we can assume that the amount of work done in each of these nodes here is equal to 1 unit. It may not be the case, but let's assume that the amount of work done in each of these nodes is equal to 1. So if you see this one on a sequential, so T1 means T1 is the time taken to execute this program, having this dependency structure on a single core processor. So that is nothing but you take a topologically sorted directed acyclic graph and execute the instructions, execute these nodes, do the work one after another. So you do a topological sort and execute. And the total time required depends upon the number of nodes that are present in this graph. In this particular graph, it so turns out that there are 18 nodes. So the total time required to execute this DAG structure is equal to 18. So this is the total work. T1 is the total work. And let's say TP is the execution time on P processors. TP is the execution time on P processors. So now, if you take the critical path in this DAG, that is the longest path in this DAG, then no matter how many processors that you deploy, you will not be able to execute this program in less than 9 time units. In this particular case, where the critical path length is 9, so T infinity, this is what is called as the span of the graph. Work is the total number of nodes present in the graph. Span is the critical path length of the graph. And it is represented as T infinity, indicating, hey, even if you employ infinitely many processors, still you require 9 time units, which is nothing but the critical path length of the in this data. So these two things are important for us. One is total work, and other is the span, Okay. So now let's say if you have two parallel structures, when we put them together in series, the total amount of work is nothing but the amount of work that you do in A plus the amount of work you do in B. And the span is also nothing but you take the critical path length in A and add it to the critical path length in B, and you get the span. So this is how we can compose two functions together in series. And if we compose the functions in parallel, then the total amount of works is still the same. You add the amount of work in A plus the amount of work in B. And but if it comes to the critical path is the max of the critical path of A and B. Okay, so that is how the span is defined. This is the parallel composition. So there are two important laws. So the first law is what is called as a work law. That is, if you deploy P processors, then you need so at least T1 by P time units to execute the whole program, to execute the whole DAG. Even if you just do the tightly, you can think of this as bin packing. No? So we have these processors P1 to P. Let me use a different notation. Maybe I'll use the word core. C1 to CP. All the work that is there, T1 units of work that is there. So you can, so you can kind of 1 to P, P plus 1 to whatever 2P, so on and so forth. This total amount of work is T1's. So TP, the time taken to execute, should be at least greater than or equal to T1 by P. This is what is called as a work law. And the span law is TP is greater than, it has to be greater than critical path. Okay, this is what is called as a span law. Are you with me here? These two are very simple things, but they are very important. So the speed up is serial time by parallel time. So T1 by P is equal to speed up on P processors. And if T1 by P is equal to P, that is, we have a perfect linear speed up. Okay. And did you get any perfect linear speed up on your machine when you are working on the BLAST programs? If not perfect, near perfect, or where do you stand? What is the best speed up you got? Of course, depends on the problem. So what depends on the cache. Huh? Mm-hmm. Super linearly got it. Okay, awesome. I would like to see that super linear speed up. Okay, it's interesting. For which problem you got it, Kishore? S dot. Huh? Interesting. Okay. Um, so if we get a super, if the speed up is greater than p, then it's a super linear speed up. But most of the time, we get sublinear speed up. Okay, so it's not almost except if you're Kishore, you don't get super linear speed up. Everyone gets sublinear speed. Okay, so yeah, I'm sorry for pulling your leg. So it's good. I'm happy to hear that, because what are the conditions that contribute to that super linear speed up, which is very difficult to achieve, is yeah, but it kind of makes sense, because when you factor in cache, and if you're able to bring data faster using the other thread, maybe it can improve the. Uh-huh. Mhm. Hmm. Okay. Okay, 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 okay. Yeah, I think all that story adds up. It makes sense. Great. So now, so here in this particular problem that we are looking at, so what is the maximum speed up that is possible? So this is very interesting, because the total amount of work T1 is equal to 18. And even if you deploy infinitely many processors, you still require, the critical path length is 9. So the maximum speed up that is possible is T1 by T infinity. So it is 18 by 9, which is in this particular case, it is equal to 2. So I think this insight that we have arrived at using an extremely simple analysis is great. Okay, because the analysis that we did so far is very simple, right? We just looked at the critical path, we looked at the total amount of work, and we are saying, hey, for this program, the best possible speed up that you can get is 2. So imagine the case if you don't have this insight, and you did all the work on, you are using a 64 core processor, and you got a 2x speed up, and you think, I am using a 64 core processor, I should get 64x speed up, and you keep on working hard, and nothing happens. So this very simple insight. So these are the things that we need to keep in mind. And I think the Silk tools, analysis tools, they give this kind of information for you. That is the maximum achievable speed up for you. When you deploy some number of processors, that kind of insight also they give. So that's where the power of the Silk tools comes. Because remember, it's just not the parallelization that solves all our problem. There should be tools which can tell us, this is the best that you can achieve, or there is a more potential. That kind of tools, analysis tools, will greatly help us in how we spend our energy. Okay. Yeah. So to summarize the discussion, so right now we are changing the notation also a bit. So that's the reason why I'm summarizing. So T1 of n, that is the total amount of work. We use W of n, that is the total amount of work in a DAG, and the critical path in the DAG, which is also called as span. So we denote it by D, D of n. D stands for depth. And so even if you employ infinite processors, we need at least this much time, and that's what this T infinity stands for. And the work law states that if you employ P processors, then no the time taken, this gives a lower bound. Okay, so this gives a lower bound on the time taken to execute the DAG using P processors, and the span law gives a different kind of lower bound. And these 2, 3, and 4 put together, we can summarize here that the time taken to execute a DAG on P processors is greater than or equal to max of these two lower bounds. So here, what we are getting is a lower bound on the computation time. Lower bound. So these are lower bounds. We are getting a lower bound on computation time on P processors. And the average, there is this notion of average parallelism. That is, if you see the critical path, so which is defined as total work divided by D of n. This is average parallelism, which says that average number of average number of nodes that we can schedule in parallel with a critical path vertex. So in order to give some intuition about this, if you have a DAG, let's say this is the DAG, this is the critical path in the DAG. So we are not going to prove this, but it so turns out. So this is, if you divide it into phases, this is phase 1, this is phase 2, this is phase 3, so on and so forth. We can do this, phase 1. So we can schedule our whole computation. We can schedule our whole computation. This is phase 1, this is phase 2, so on up to phase D of n. A nice theorem for you to prove is, if you look at other nodes in the graph, we can place those nodes in the graph in such a way, in these different phases, and we can keep these nodes in such a way so that there are no intraphase edges. That is, there are no edges from here to here. If there are any edges, they go from here to here or from here to here, but there are no intraphase edges. So it is possible to take this DAG and take the critical path in the DAG and divide the whole computation into D phases. And we can, the rest of the nodes that are present in the DAG, we can place them in different phases in such a way so that there are no intraphase edges between them. So that's a very important thing, because all the nodes that are present in the same phase, they can be scheduled in parallel. Are you with me here? So here all the nodes that are present here, like for example, if this is later on, we will see a formulation. So if W1 is the number of nodes in the phase 1 and W2 is the number of nodes in phase 2, so on and so forth, then the total work W is equal to sigma I is equal to 1 to D of n Wi. This is the total work that is there in this diagram. And what is the total time taken if you deploy P processors? Time taken using P processors is equal to sigma I is equal to 1 D of n Wi divided by P C. Does this make sense, this summation? So the amount of work in each phase is Wi, and if we deploy P processors, then we can then the total time taken is equal to TP is equal to this particular. Okay, and this is what we will see in little bit more detail now. Okay, so this is what, so we are now looking into what is called as a Brent's theorem. The total amount of work Wn is equal to K is equal to 1 to D, Wk, where Wk is the amount of work that we do in the kth phase of computation. And TP, yeah, so when we deploy T processors, time taken is given by this thing. Okay, does this make sense, these two equations? So, so now what we do is, if you remove this ceiling, Okay, if you remove this ceiling, so wk by p with ceiling, we can kind of upper bound it. We can replace it by this no by this value. We can replace this inequality with an inequality. And earlier we were looking at the lower bound. Right now we are looking at an upper bound, and this is what we get. Okay, and when we do this, simplify this summation, what do we get? What do we get here? This is equal to what? Can we, in the numerator, all wk's gets added up, and we get a w, and then denominator will have a p, and then we have this one goes for d times. Yeah, so actually I think I made a mistake. Yeah, this should not be equal to wk by p. This should be, this is wk minus 1 by p. When you remove this ceiling, the inequality is wk minus 1 by p plus 1. Don't worry too much. All it says is this is I think this, I'm not sure about this, but when you remove this ceiling here, then what with the upper bound turns out to be this. This is wk minus 1 by p plus 1. This is what we have. And when we expand this summation, so yeah, so this is we get this. Okay, it makes sense, right? So you add one d of n times, so this will result in this when we take the summation inside. And similarly, when we take the summation inside, you can take it, we can take the summation to 3 places. The first summation, it will lead to the total amount of work. The second summation, so it's just one taken d times, so it is d of n. And the third summation is also d of n. So this is the simple thing. So the interesting thing now is, so now when you simplify this further, this is what we get. So this, what we have here is the lower bound, and what we have here on the right side is the upper bound. Okay. And how can we rewrite this? Can we rewrite this as follows? W of n divided by p plus d of n into p minus 1 divided by p. Can we write this one? Both are equivalent, right? And so can we approximate this p minus 1 divided by p to 1 and kind of leave it out? So this one can be approximately be equal to 1, and we can leave it out. So this is what is called as a Brent's theorem. What you are seeing here, this is Tpn is less than or equal to Wn by p plus d of n. This is Brent's theorem. Okay. Are you all with me here? So it so turns out that the upper bound and the lower bound are within a factor of 2. Okay, you can see here in the lower bound, definitely Wn by p is there, right? Wn by p is there in the lower bound, and in the upper bound we have Wn by p plus d of n. That means if you stretch by a span in time, definitely you will be able to do all the computation. This is the best that you can do. No, but it's just not that we will be able to finish the execution within this time. And this is what is called as a what is called as Brent's theorem. Okay, if you go see online, in many places Brent's theorem is stated like this. Okay, this is how Brent's theorem is stated, upper bound on the computation. Okay, T1 is nothing but the total work, and T infinity is nothing but the span, and this is how it is. So why is this important is when you do your computation, when you are building a runtime environment, okay, we are now looking at the whole thing from a programmer's perspective. Let's say if you are building a scheduler, what is your goal as a scheduler, as a person who is writing, as a programmer who is writing a scheduler? Your goal should be that if you're crossing this upper bound, then that means you're not doing a good job. Then that means you're probably not optimal. Yes or no? If you are not able to do work within this upper bound, then that means your scheduler is probably not optimal. You are taking more time than a theoretical upper bound that we have on the time taken to execute the program. Okay. Shall we move on? All good? Okay. So now we will look at some interesting, to conclude this thought process. So we will see um, the notion of what is called as a work optimality. So let's assume, so usually what we do is, if you take the same serial program and when we try to parallelize it, it may not be a good approach to solve that problem. So what do we do when we move from an algorithm which is designed for sequential execution and try to parallelize it, instead of blindly trying to uh, look try to see what you can do within the context of that sequential program. Sometimes you may want to rethink the algorithm itself. Okay, sometimes you may want to come up with a different algorithm which is more suitable for parallel execution. Are you with me here? So there is this algorithm which is extremely good for serial version if you are executing it on a single core, but if you want to parallelize it, it's a nightmare. Okay, but or it's a nightmare, or it doesn't work also. Maybe the span is too high for that serial version of the code. Okay, so one of the things that we want to do when we want to parallelize a program is we want to reduce the span, right? Like for example, if you want to sum up the elements of an array, if what is the baseline serial code that we write, so for I is equal to 0, I less than n, plus plus I, s plus is equal to a of I. Okay, this is what we write. And if you think about it, so if you look at the things, so you have an addition operation here, s comes in here, and then you have a of 0, and then the sum goes again here. You have a of 1 here. These are all, these nodes represent addition operations, and a of 2, so on and so forth. So if you look at this DAG structure, what is the span of this DAG? What is the span of this DAG? N, right? So it's n, the span is n. So if you want to parallelize this, it's not going to happen. Okay, you have to change your algorithm structure. And what is the work done? The work done, Wn is equal to n, some n additions. So if you want to parallelize this program, then so you want to construct a reduction tree. You can take these two nodes and you add them up. You take another two nodes, you add them up. So you can construct a reduction tree. And when you take a reduction tree approach, what is the work? What is the work of this this reduction tree algorithm? The work will be the same. Okay, total number of additions will be the same. Yes or no? I'm not sure. Maybe it should be the same. Because the number of leaves are n. If it's a tree, then the internal nodes will be n minus 1. Every internal node constitutes an addition, so the number of additions remains the same, so that the work remains the same. But what is the span? What is the span of this reduction tree? It is log n. So when you want to parallelize a program, so instead of just taking the serial version and try to grapple with it, sometimes you may want to think about it, the problem differently, so that you can reduce the span, and that permits you to parallelize the program, perhaps. Okay. And the speed up is defined as the best serial time versus the parallel time that you get using P cores. So once you get into research, which many of you know, will soon, what people will do is they don't take the best serial time. Okay, they just write some code and they think of it as baseline, and they spend all their energy on parallelizing, and they say they got 10x speed up or 20x speed up. Uh, but if you actually think about it, the same amount of energy, if you put it in the serial version of the code to optimize it, perhaps you may, instead of getting 10x speed up, you may get 2x speed up, but it's not good for research papers, so you don't. Okay, so usually, what happens is, again, so 10 years back, when GPUs are becoming very, very popular, so the lot of research is on how a particular algorithm performs super fast on GPU when compared with CPU. People, what they usually do is they spend 6 months to 8 months of time trying to optimize their code on GPU, and they just take some baseline version on CPU and they show that the GPU version is 20x faster or 100x faster than the CPU version. But that's not a fair comparison, because if you spend 6 months of time on the CPU version also, perhaps you may instead of getting a 100x speed up, you may just get 2x speed. Just watch out. Okay, so but in any case, so that's a side note. The point here is, when you want to parallelize things, so keep a note on this. Okay, so there is a you want to reduce the span in order to expose parallelism, but during this process, instead of doing W, instead of doing N work, you may end up doing N square work or N log N work. You increase the work, but the cost but the gain that you pay by increasing work, but you gain by decreasing span. Are you all with me here? There's a program that you want to parallelize, and during the parallelization process, you are willing to kind of slightly increase the work that you are doing in order to expose the parallelism and reduce the span of the program. So here, how much more work you are willing to do, how much more work you should do during this process, and what is the cost of increasing the work. These insights we get when we take a deeper look at this analysis. So again, remember, T star n is the best serial time, TPN is the parallel time, and W star n is the work done by the serial version of the program. Okay. So now, if you see this, if you kind of simplify this one, so what you have is, W star n, and remember in the, if you go back, so what do we have here? So here, when we simplified it, what did we get? We got W plus W by P plus D. That's all. No? This is what we get. That's true. We got P minus 1 by P, but we said, no, let's approximate it to this is equivalent to 1. So W by P plus D. So here, what we are getting here is a clear, yeah. So this is equal to W by P plus D. Does this make sense? W star n I just want to see W plus, no. This is true only. Is this simplification right? Can you check this? W by P plus D into P minus 1 by P. It looks right only. And this, if we kind of approximate it to 1, what we get is W by P plus D. Okay, great. something is okay. Let's use this one and do the analysis. And d by del. Something is not adding up. I have to check because TP W by P plus. Okay, let's continue this. Okay, let's do the simplification and see what happens. Okay. Um, yeah, I think we are doing all right. Okay, so what happens is, let's remove this. Let's assume that this n is all the time there. So what we have is W star divided by, please pay attention. This is, we would like to get something interesting out of this. This gets simplified to W star times P divided by W plus PD. Okay, and this gets simply, if you take this P down, or if you keep this P up here and take W star down, so what we get is P by W star plus yeah, I think we are doing good. Yeah, so D by W star divided by P. Is this equivalent, right, to above? Does this make sense? Are you with me or lost here? Not very, it's very simple only. It's, except that my handwriting is bad. It's apart from that, it's simple. So you have a P going to numerator, and we are bringing W star to denominator, and we are rewriting it differently. Yes or no? How many of you are with me? Can I see? Make sense? So now, what is the goal? The goal here is, if you see, in order to get get a perfect linear speed up, or close to linear speed up, we want the denominator to be close to 1. Okay, close to 1, or it should be constant, some constant. Or even if it is constant, it is great. The reason why it is great if it is constant is, even as the value of, let's say, if the numerator contains n, what will happen? Sorry, if the denominator contains n, what will happen? Some function of n, like square root of n or log n. Even if, let's say, if the denominator contains log n, the problem is, as the problem size increases, the speed up that you can get goes down. Okay, but if the denominator is constant, even if the problem size increases, let's say if the denominator is equal to 1 or 1.2 or something like that, then that is great, because even if the problem size increases, the speed ups that we are going to get remains the same. We get constant speed ups. Okay. In order for that to happen, you can see this W by W star, it has to be equal to a constant. That is, when you are moving from serial code to parallel code, the work cannot increase by a factor which is a function of n. You can increase the amount of work that you are doing when you are moving from serial code to parallel code by a constant value, but it cannot be like you are doing log n more work. If you are doing log n more work when we are going from serial to parallel, then asymptotically it's a bad thing, because as the size of the input increases, the speed up that you get will go down. And this is what is called as work optimality. So this is a super important thing, because when you come up with a parallel algorithm for a serial code, what is the first thing that you should check for? You need to check if it is work optimal or not. If it is not work optimal, your program has a very poor, your parallel program has a very poor speed up scalability property, because as the value of n increases, this W by W star, it will be something like log n or even log n also. It's going to be bad for you because your parallelism, the achievable parallelism goes down. Okay, that's number one. The second factor, if you see, we would like to compare D with W star by P. Okay. So what this says is W star by P is the work per processor. The work per processor should grow proportional to the span. The work per processor should grow proportional to the span. Otherwise, again, what can happen is, you will end up having some function of n in the denominator from here. Again, it will have a poor, it will end up giving it poor scalability property. Okay. If you think about it differently, if you think about it intuitively, what it says is, the amount of parallel work, think of how your span is increasing as your program input length is increasing. If your span is increasing, but the amount of parallelism is not increasing, it's bad. Yes or no? Span is increasing, but the amount of parallelism, the amount of work that you can do per critical path step, if it's small, again, it's a bad thing for you. Okay. So that means whatever that you are investing, in increasing the span, or you need to see that uh, the work per processor also grows in line with the span. So I think the second one is little bit less intuitive, but the first one is, very simply you can check. Okay, what is the work, whether your parallel program is work optimal or not. Okay, can you give an example of a problem where the parallel algorithm is not work optimal? Can you think of a? Is there any program you have encountered? You can think of a problem and it's see parallel version, but you think the parallel version is not work optimal. Think about it. It's a nice question. But this is a whatever the so this is the summary of today's class. The summary of today's class is, if you see here, we are able to get lower bounds here using work and span laws. Okay, that's number one. The second idea is the notion of average parallelism. Okay, work by divided by span. And the second idea is this is the Brent's speed up theorem, which gives an upper bound. Remember, the upper bound is written in a different way. The upper bound is T1 by P plus T infinity. This is the upper bound. Okay, so this is how Brent's theorem is usually stated. This is, you are getting an upper bound. If you are writing a scheduler which violates this upper bound, then that means your scheduler is not a great scheduler. That's the second point. The third point on when we are trying to come up with a parallelization strategy, and you are comparing your parallel program with your serial version, there are two things that you need to keep in mind. The first thing is your parallel program has to be work optimal. That means originally, if you are doing some X amount of work, you can do 2X amount of work or 3X amount of work. All those things are to some extent okay, but it cannot be, you cannot increase the amount of work that you are doing by log n factor or log n factor, because when you do that, those factors will creep in here and the achievable speed up goes down. This is the work optimality principle. This is a very easy thing to check, and you should very nice property to keep in mind, check to keep in mind when you are trying to parallelize programs. The second is weak scalability. This is slightly less intuitive. So here what we are doing is, instead of this whole thing, what we try to do is, so we have written this as D by W star divided by P, and we are comparing, yeah, so sorry. And we are comparing this whole thing, lower, this whole thing with the numerator. Okay, that is, as the value of, as the input length increases, the span increases. It's okay if the span increases, because it will increase, but make sure that the total work, that the average, that the work done per processor also proportionately increases. If that doesn't increase, then no, it's not good for you. Okay, you'll end up paying penalty in your potential speedups that you can achieve. Okay, so with this, I will stop the first part of today's